Welcome back to this next video in which we are discussing groups of order PQ. Okay, so we're making the assumption now that we have a group of order PQ where the smaller prime p does not divide the larger prime q, subtract 1. And the claim that we've now made is that if this is the case, then you can instantly say that your group is going to be isomorphic to the cyclic group on the set of p times q elements, i.e. there's only one isomorphism class of order p times q for p does not divide q minus 1. Okay, right, so what we want to now do is attempt a proof of this. Okay, now as I said at the end of the previous video, the proof of this is quite a tricky little argument, okay, when you see it for the first time, but it will teach you a lot of good tricks in group theory. Okay, so we're going to show it. So, how are we going to do this then? Well, firstly, let's try and characterize the elements of the group capital G. Okay, now we know that we have these two subgroups, P and Q, these two interesting subgroups, capital P and capital Q, that are both normal subgroups in the group capital G. We also know that this one has order little p a prime and that this one has order little q. Now that means that both of these are cyclic subgroups. So p is going to be a cyclic subgroup, and let's say it's generated by some element little x, and q is going to be some cyclic subgroup, and let's say it's generated by some element little y here. Okay? Now, the next claim I want to make is that actually the intersection of these two is going to be equal to the trivial subgroup. So because they're both subgroups, we know that when we intersect the two we'll get another subgroup. But my claim is that it has to be equal to the trivial subgroup. And the reason is that both of these subgroups here contain, well, they're both isomorphic to a cyclic group on a set of prime number of elements. So this one's isomorphic to a cyclic group on the set of little p elements, and this one's isomorphic to the cyclic group on the set of little q elements. And we know a lot about these sort of groups. We know that these groups, their elements will have order either equal to 1 if you're the identity element, or they will have order equal to the entire group because of Lagrange's theorem. They must, all of the elements in the subgroup, all of the non-identity elements in the subgroup must generate the entire group, basically. So all of these, all of the elements inside this must generate the entire subgroup if you were to generate their cyclic subgroups. Okay, so they'd all have order p, and the same for this. All of the non-identity elements would have order q in here. Okay, so that means that only the identity element can be shared, because all of the non-identity elements here are of order p, all of the non-identity elements here are of order q, so they can't possibly be of order p and q, so none of the non-identity elements can be shared, so the only shared element is the identity, and therefore when we intersect these two together we're going to get the trivial subgroup. Okay, now, we also know that both of these are normal subgroups, and actually what this allows us to say is that when we product the two subgroups, so when we take the product of p and q, and if you're not familiar with this, please do watch the video on the product of two subgroups. So when we product p and q together, we must actually get a subgroup of G, okay? And because the order of the intersection of p and q is equal to 1, then the order of this is going to be equal to the order of p times the order of q, and therefore it's actually going to be equal to the entire group capital G. Okay, but I'll repeat the argument as to why this has to be a subgroup. Because both of these are normal subgroups, we know from the video on products of two subgroups that if just one of them is a normal subgroup, it doesn't matter whether the other is a normal subgroup. If just one of them is a normal subgroup, then you can instantly conclude that no matter what the other one is, then the product of the two will be a subgroup. Okay, and we know that the order of the product of two subgroups is going to be the order of the two subgroups times one another divided by the order of the intersection of the two, again from the video on the product of two subgroups. Therefore we can conclude that the product of P and Q is going to be equal to the entire group capital G. Now what is the product of P and Q? Well, the product of P and Q is the set which consists of all elements of the subgroup capital P composed with all elements of the subgroup capital Q. Now all elements of capital P are of the form x to the power of I, where I is equal to 0, 1, 2, all the way up to P minus 1. All elements of the subgroup Q are of the form a power of y, so y to the j, where j is equal to 0, 1, all the way up to Q minus 1. Okay, so I is going to equal 0, 1, all the way up to P minus 1, and j can equal 0, 1, all the way up to Q minus 1. Okay, and all of these things together, that is going to form the product of P and Q. Okay, and of course the order of this set is going to be P times Q. You've got P possibilities for I, Q possibilities for j, so all of these are going to be individual, that they're all going to be distinct, and they're all going to be corresponding to a single element of capital G. Okay, right, so this beautifully characterizes the elements of capital G. I now know that any element of capital G can be written in this form, a power of x composed with a power of y, and that's very, very helpful. Okay, so that's some of the way towards actually understanding this group. Okay, now, although I've now characterized all of the elements of the group, I can say, okay, every element of the group is a power of x times a power of y. It doesn't actually help me understand the composition law on the group, okay, because I don't know how to compose two elements together. I can write every element now as a power of x times a power of y, but that doesn't tell me how to compose two of them together to get another element in the form a power of x times a power of y. It would, if I knew that the group was abelian, then it would be brilliant. Okay, I'd know completely how this works. Okay, and my claim is that it's going to be abelian, but we will need to prove that. Okay, so if it was abelian, I'd be in business, because I'd know exactly how to compose any two elements together. Any two elements could be expressed as a power of x times a power of y, and then all I'd need to do is add the powers of x together modulo p, and add the powers of y together modulo p, and I'd be in business. I'd have a complete understanding of my group capital G, and indeed I'd be able to prove that my group was isomorphic to the cyclic group on the set of P times Q elements. And the reason is, if you consider the element x composed with y and ask what is the order of that element, what's the lowest power that I'd have to raise this element to in order to get the identity back again, I claim that that would be equal to P times Q. And the reason is that I'd need to raise it to some multiple of P in order to make the x equal to the identity, and some multiple of Q in order to make the y to the power of something the identity. So I'd have to take the lowest common multiple of P times Q. Now, because both of them are primes, the lowest common multiple is just going to be the two of them multiplied together, because if they're both primes, they're clearly going to be relatively prime. Okay, and therefore their greatest common divisor is equal to 1, and their lowest common multiple will be P times Q, just the two of them multiplied together. Okay, so the smallest power that I would have to raise this element to get the identity would be P times Q, and therefore, of course, I would get every single element in here on my journey to try and get this back to the identity. Okay, so indeed x times y would generate the entire group capital G, and therefore I'd be able to conclude that G was isomorphic to the cyclic group on the set of PQ elements. Bingo! So all I need to now prove is that it's abelian. That will tell me how to compose this together, and if I know that that's the way that I compose it together, just by adding the powers of x and adding the powers of y, modulo p and modulo q respectively, then I can conclude that this element x composed with y is of order pq, and therefore that my group is isomorphic to the cyclic group on the set of pq elements. So all I need to prove is that it's abelian. So how am I now going to prove that it's abelian? Well, to prove that it's abelian, all I actually need to prove is that x and y commute. All I need to prove is that x composed with y is equal to y composed with x, and the reason is I've already proven that every single element of the group can be written as a power of x times a power of y. So if I want to compose any two elements together, I'll just write them in this form, a power of x times a power of y, both elements. And then, of course, if all of the x's and all the y's commute, then the two elements will overall commute. Okay, so all I actually need to prove is that x composed with y is equal to y composed with x. So how am I going to do that? Well, this is the part that you're not going to expect. This is the strange bit of the argument, okay, that you're just going to have to bear with it, okay? The way I'm going to prove this is by proving that the centralizer of the subgroup capital P, which remember is this one and only subgroup of order little p here, is equal to the entire group. And by proving that, I will prove this. Proving this will prove this. Okay, let me explain why. So just let me remind you of the definition of the centralizer of P and G, and I'll just move this up a little bit. Okay, so the definition of the centralizer of P and G is that it's all elements of the group, and I'll use little s to denote an element of the group. So for all, it's all the elements, little s, in the group capital G, such that if you use little s to conjugate any element of the subgroup capital P, it fixes it. Okay, so S inverse has to equal little r for all little r is an element of capital P. Okay, so it's all the elements of the group which, when they're used to conjugate the elements of capital P, fix each and every one of the elements of capital P. Now, clearly, if the group is abelian, then it will be true that the centralizer of P and G will equal G, because conjugation has absolutely no effect in an abelian group, and therefore all elements will satisfy this condition. However, it's also true that if I can show that this is true, then I've proven that this is true, and therefore that I've proven that it's abelian, because look, little x is an element of capital P. Okay, little y is an element of capital G. Okay, proving this is equivalent to proving that little x is x, y inverse, i.e. that y is an element of the centralizer of P and G. Okay, because if y was an element of the centralizer of P and G, then it would fix little x, which is an element of P. It would also fix all the other elements of little p. Of capital P. I don't care about that. I just want to know that little x is fixed. So if I was to prove this, it would prove that this is true, and therefore it would prove that this is true, and therefore it would prove that this is true. So I'm going to dedicate all of my effort now into trying to prove that the centralizer of P in G is is the improper subgroup of capital G. Now, how am I going to do this? I'm going to prove it by contradiction. Okay, so we're going to assume that it's not the case, and then we're going to arrive at some rubbish. Okay, so we're going to assume then that the centralizer of P in G is not equal to the entire group. Therefore, what must be the order of the centralizer of P in G? Well, we know that the centralizer of any subset in the group is always going to be a subgroup of the group. Okay, so by Lagrange's theorem, it must have order 1, P, or Q. Okay, because we're saying now that it doesn't have order P times Q. Okay, so those are the only possibilities now for the order of the centralizer of P and G. Okay, it must be order 1, order P, or order Q. Those are the only possibilities. Okay, now, what we're going to do is we're going to consider quotienting the entire group out by the centralizer of P and G, and we're going to study that quotient group. Now, if we can do that, then it must be the case that the centralizer of P and G is a normal subgroup. Okay, so that's what I'm going to dedicate my effort to now, showing that the centralizer of P and G is always a normal subgroup, provided that P is a normal subgroup, and that's why we require that P is the only C log P subgroup. Remember, you might be wondering, where are we actually going to use this part? Okay, well, this part allows us to conclude that there's only one C log P subgroup, i.e. that C log P subgroup is normal. Okay, now we're going to use the fact that C log P subgroup is normal. Okay, so next claim, or mini lemma, let's have a mini lemma here. Okay, so the mini lemma is that if P is a normal subgroup of G, okay, which indeed we know it is, don't need an and actually, then the centralizer of P and G is always going to be a normal subgroup of G, and therefore we will be able to quotient R group capital G out by the centralizer of P and G, and that's how we're going to arrive at a contradiction, by studying that quotient group that we'd end up with and realizing that there's something ghastly wrong here. Okay, right. So let's prove this then. So, but how am I going to prove then that the centralizer of P and G is a normal subgroup of G? Well, of course, the definition of being a normal subgroup is that if you conjugate this subgroup by any element of the group, it has to give the subgroup back again. Now, because we're working in finite group theory, it is enough to show that, let's say, for all S is an element of the centralizer of P and G, we need to show, and for all G is an element of capital G, we want to show that GS, G inverse, is an element of the centralizer of P and G. It's enough to show that, okay? The reason is that conjugation of the entire group capital G by little g is an injective map. It will be an inner automorphism, and therefore it's going to actually be a bijective map, but it's certainly going to be an injective map. So when you restrict it down to this restricted domain, which is the centralizer of P and G, okay, which is this subgroup of G, it's still going to be an injective map. So if we can prove that all of the elements of the centralizer of P and G are mapped back into the centralizer of P and G by this conjugation map, then we know that it must be injective, because on the larger group it's injective. So we've got an injective map from the centralizer of P and G into the centralizer of P and G. This is finite group theory, so both of these are finite sets, okay, and therefore if we've got an injective map from here to here, they're both of the same order, it must therefore be surjective, okay, basic finite set theory here. Okay, and therefore it's going to be bijective. So that's why this suffices in this case. It's because we're doing finite group theory rather than infinite group theory. Okay, so all we need to show is that if we conjugate any element of the centralizer of P and G by any element of the group, we end up with an answer that is again in the centralizer of P and G. Okay, so we just want to make sure basically that GS G inverse is going to actually fix all elements of P. Okay, so let's use this element to conjugate the elements of P, okay, and see if we always get the answer fixed. Okay, so we're going to now conjugate an element which I'll call little r, which is an element of capital P, by GS G inverse. So what's the inverse of GS G inverse? Well, it's going to be G, because G will cancel with this, then we'll want S inverse to cancel with the S, and then we'll want G inverse there to cancel with the final G. So hopefully you'll agree that's the inverse of this one here. Okay, so I'm now conjugating my arbitrary element of capital P by, my arbitrary element of capital P in the middle here, and I should colour code it. Here's my arbitrary element of capital P in green, by this element of the centralizer of P and G. So S, remember, is in the centralizer of P and G, so we know it fixes all the elements of capital P when it's used to conjugate them. Which has been conjugated. So we're now conjugating R by a conjugate of S. Okay, and we want to prove that this is equal to R. So, G inverse RG here, that's effectively conjugating R by G inverse. Now, because P is a normal subgroup, I know that whenever I conjugate any element in P by any arbitrary element of the group, which G inverse is, then I'm going to get something in capital P. So yes, this might not be equal to R, but it is going to be something in capital P. This is the reason I require P to be a normal subgroup in G, okay? Because if it wasn't a normal subgroup in G, I wouldn't be able to make this conclusion here. And I need this conclusion, that when I conjugate R by G inverse, it stays in capital P. It might not stay as R, but it does stay in capital P. Okay, then I'm taking this element of capital P here and conjugating it by S. Okay, S is in the centralizer of P and G, so whatever element of P you conjugate with S, okay, it's not going to change. So we might as well just get rid of this bit. Okay, it doesn't change it, it stays as G inverse RG. And then look, we're now conjugating by G. We're just going to invert it now. G will cancel with G inverse, and G will cancel with G inverse on this side, and of course the overall answer will equal R. So it will reverse it back to R. Okay, i.e., and that's true no matter what R in capital P. I didn't make any other assumptions about little r. It's an arbitrary little r from capital P, and this argument would hold for any little r as an element of capital P. Okay, so truly, you take any element of the centralizer of P and G, provided that P is a normal subgroup. If you conjugate that by another element of the group, okay, you will get another element that is in the centralizer of P and G. Okay, so the centralizer of P and G is going to be a normal subgroup, provided that P is a normal subgroup of G. Okay? Done. So the centralizer of P and G is indeed a normal subgroup. So what we can now do is we can take G and we can quotient it out by the centralizer of P and G. Okay, so we can form this quotient group, and the first thing to say is what is going to be the order of this subgroup? The order of this quotient group. Well, of course, it's going to be the index of the centralizer of P and G in G. Now, the order of the centralizer of P and G was equal to 1 or P or Q. So the index of the centralizer of P in G is just going to be the order of G divided by these possibilities. So it will either equal P times Q if the order of the centralizer of P and G was 1, or it will equal Q if the order of the centralizer of P and G was equal to P, or it will equal P if the order of the centralizer of P and G was equal to Q. Okay, so those are the possibilities for the order of the quotient group that we've ended up with here. Okay, now have a break there, go over this argument for yourself, because as I say, you might not have seen the fact that if P is a normal subgroup, then the centralizer of P and G is going to be a normal subgroup before, okay? And in the next video, what we will do is we will study this quotient group in more detail, and we will use it to arrive at a contradiction, and we will be using the fact that this has order P times Q, Q, or P, i.e. it doesn't have order 1 if we're making that assumption that the centralizer of P and G was not equal to G, which is of course the thing that we're hoping to disprove.